All right, so we're jumping to chapter 9. Chapter 9, I usually do at the very end because there's a lot of it on the AP exam, BC exam. And by doing it at the very end, I want it to be the freshest in your head. Okay. It's also the part where students tend to get a little bit mentally discombobulated because there's a lot of, there's some memorization that goes on, but what else is new? And then we summon kind of the powers of infinity. And sometimes that can be very paradoxical. It can be a paradox. Yeah. Right. So the ideas themselves are kind of like really heavy. But I'm doing it now because it seems like every year people always say, man, I wish you would have spent more time on sequences and series. And then the other stuff that I need to come back to, which is polar and parametric, and then chapter 6, which is volumes of solids in area. I think we can get those pretty easily or manage those somehow in another way. So anyway, here we are, chapter 9, the last chapter. It's a big chapter. It's a fun chapter. We're not quite finished building the second half of the House of Calculus, but we're putting that project on hold, and now we're going out back and we're building ourselves a nice man cave, a nice she shed, a nice tool shed, if you will, for all of our mathematical tools. So it's entirely different from derivatives and integrals, although they are related and they are kind of built on the same foundation of the idea of the limit. So any comments before we start? Sequences and series. Okay, very good. So let's look some. Let's do some terminology. A sequence, right? Outside of a math class, y'all know what the word sequential means, right? It kind of implies order, doesn't it? In sequence, line up in sequence, whatever. And that's all a sequence is. It's a list of things generated by a rule mathematically, and the order matters. Order matters. Order matters for a sequence. All right. So if I went like this, let's go up and down the aisles and call out numbers, the multiples of 2, 2, 4, 6, 8. The sequence would matter. If I prescribe how to do it, let's snake up and down, the order would matter. That would be your sequence, right? 2, 4, 6, 8. Who do we know appreciate? That would be a sequence, right? That's an example. Now, the rule that would generate that sequence is give me a multiple of 2, right? That's a positive integer. And then someone give me the very next one, very next one. So here's how we write that. More formally, a sequence is a function whose domain is the set of positive integers or natural numbers. Remember the natural numbers? We use this right here. That's the set that is equal to this. It's the positive whole numbers. 1, 2, 3. And that itself is a sequence, right? Because what would the next number be? 4. And the next number is 5. And what does the dot, dot, dot mean? It goes on to infinity. So this is an infinite sequence, right? Some sequences are finite. Like if I just listed the first 10 natural numbers, it'd be 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. That would be a finite sequence. The whole set itself is an infinite sequence, but the order matters. If you have 1, 2, 3, 5, then it's like, no, you went out of sequence. You went out of order. That's not very good. Okay. Now notice I listed 1, 2, 3. It was pretty easy to know the next number is 4. What if I would have just said 1 comma? Would y'all have known what came next? No, because it could have been this. It could have been 1, 1, 2, 3. And what would the next number be there? 5. What sequence is that? That's the Fibonacci sequence where order matters. You start with 2 rabbits, 1 plus 1, you get 2 rabbits. 2 rabbits turn into 3, then 5. This actually grows faster than exponential in the long run. All you're doing is you're adding the previous numbers, okay? After you start with your seeding values of 1 and 1. So that would not be the natural, that would be the Fibonacci. But that's what a sequence is. Order matters. Order matters. And we list them, we separate them with commas, okay? So we call the items in that list terms. So the terms in the previous Fibonacci sequence would have been 1, 1, 2, 3, 5, 8, whatever. So A sub 1, A sub 2, A sub 3, A sub n. Now notice this is the abstract. A sub 1 is the first term, A sub 2 is the second term. We use the subscripts here as counters, okay, to keep track of which term it is, up through the nth term. We call this right here the nth term. So far, so good? All right. So that's why we say the domain is natural numbers, because the first term, whatever the number is going to correspond to an input value of 1. The second term, whatever the number is, whatever the output is, it's going to correspond to the input of 2. It's the second term in the sequence. All right. So there it is. A sub n is the nth term. By the way, we also call the nth term the rule of sequence. The rule of sequence. They're really interchangeable, and you'll see that when we get to power series, that I kind of refer to them both in the same class period. All right, so how can we express, or how can we define a sequence? Well, you can either give an ample number of terms in the sequence. What do I mean by ample? A lot or enough is a good substitute. Yeah, you need to give enough terms in the sequence separated by commas. Like here would be the example, right? The example would be 2, 4, 6, right? 3 is the minimum. 3 is the minimum. If it's a simple sequence, you put 3 there, most people are going to figure out what the fourth one is. The more complicated the rule, the more terms you'll need, right? They turn into like little puzzles, like guess the missing number, right? Well, you need more information. So the minimum number is 3. You separate them by commas, and then you put your ... which are called ellipsis points. And then, of course, we set them off with braces, which defines the set itself. So that's one way to represent a sequence. You can also define it by a rule of sequence. In other words, A sub n is equal to n plus 1. Okay, that's another way to do it. Now, what would that sequence look like? This sequence, if I wanted to generate it like that, it would be what? What would be the first term? 2, right? Because we always start with n. They're called natural numbers because the idea of 0 wasn't even around. Cavemen didn't walk around wondering, telling themselves, man, me wish me had rock. Me have no rock right now. Me wish we had rock. Caveman had no idea that rock even existed. You know, he didn't walk. I don't walk around saying, I wish I had a Jabberwocky right now, because Jabberwocky, what is Jabberwocky? It doesn't even exist. Actually, it does, right? But it doesn't exist until you see it. And then when you see it, you have it. So the first counting number or natural number is 1 naturally, right? So the first term would be 1 plus 1, which is 2. The second number when n is 2 would be 3. The third number when n is 3 would be 4, so on and so forth. Okay, 2, 3, 4, right? So these two now are interchangeable. They represent the exact same sequence, right? Okay. Or you can set it off in braces. That's what I have there. An ample number term, the sequence. Yeah. So I don't know why yeah. It's really 2 ways. And then the third is just, I need to modify that. Whenever you list them, you set them off in braces like that. Now, if you want to give this a name, you can still call that A sub n. All right. You can name the set. You don't put colons there, you put equal signs. The set is that. The set of natural numbers is 1, 2, 3, ... Okay. They're interchangeable. All right. Sequence. Got it? Order matters. Order matters. All right. So if we look at the sequence 2, 4, 6, 8, those are the set of even numbers. So if I wanted to represent it, it would be like this: 2, 4, 6, 8. I don't really even need the 8. 3 is the minimum. I don't want to put 2, 4. If I call this A sub n, one of the main things that we're going to have to do is we're going to have to figure out the pattern. That's why this section sometimes can be a little bit too much fun, because we have to figure out a pattern. That is, we have to figure out the formula in terms of natural numbers that generates that. What is the rule? What's the mathematical rule that generates those? N times 2. So it could be equal to what? 2n? Would that work? That looks good to me. Let's try. When in doubt, try it out. When n is 1, we get 2, right? When n is 2, you get 4, right? When n is 3, you get 6. So that works, yes? Well, that's fantastic. Boy, yeah. So this is nice to have this, because we can predict the next term recursively. Okay. Let's talk about that. We can predict the next term. This is an important word, recursively. Recursively just means that it relies on the previous term. Like the Fibonacci sequence, that's a recursive sequence. You have to add up the previous two terms to get the next term. Okay. But the holy grail of mathematics is to try to get this. This is the holy grail, because we don't have to generate an element of the set or a term in the sequence recursively. This is an explicit formula. Okay. And you can't always find that. There is no explicit formula for the Fibonacci sequence. You have to do it recursively. Okay. But we do have a holy grail explicit formula for the set of even numbers, don't we? So like if I wanted to figure out what the fifth even number is, I don't have to count on my fingers, 2, 4, 6, 8, 10. It's 10. I could do that. Or I could just say, oh, you want the fifth one? 5 times 2, it's 10, right? But I can't say what's the fifth Fibonacci number and have you plug it into a formula. To get the fifth Fibonacci number, you have to be, okay, it's 1, 1. It's always seated with 2 rabbits, 1 and 1. And then you add them up, 2, 3, 5, 8, 13, so on, 21, recursively. So 1, 2, 3, 4, 5. This would be a sub 5. It's the fifth Fibonacci term. There's no formula for it, okay? So you don't always get the formula, but you can. Now, let me modify this. What if I want to look at this set, okay? What if I have this set? I'll call it K for kooky corpy, okay? What if it's 4, 6, 8, ... I maybe put one more in there. You're allowed to put, if it's a simple sequence, you're allowed to put more than 3 if you want. 3 is the bare minimum. What would be the next number? 12. Okay. 14, 16. Can I figure out what K of n is, the formula that generates it in terms of the natural numbers? Is it still 2n? Well, I don't see. When n is 1, what do I get? When n is 1, I get 2. Oh, plus 2. Well, that's different. 2n, does 2n plus 2 work now? Let's see. When n is 1, I get 2 is 2 plus 2 is 4. So if it works for the first one, is it guaranteed to work for all the rest of them? No, no. Let's see. When n is 2, what do I get? 2 times 2 is 4. 4 plus 2 is 6. Okay. Okay. And then when n is 3, 3 times 2 is 6. 6 plus 2 is 8. Okay. Boom. We got it. We got it. We got it. Is that the only way to do it? No, you could have just said, hey, let's just offset n by 1 like that. Now, does that work as well? Yeah, high five, right? Because that's the same as just factoring out the 2. But now you could say, oh, when n is 1, let me plug it in. Now I'm starting at 2 and I get 4. So there's sometimes more than one way to think about it, more than one way to get it, but algebraically it works, okay? So real quickly, instead of using f of x equaling 2x plus 2, where x is going to be an element of the real numbers, that's what we've been studying up to now. We write it as a, you could do a of n, but typically we write it as a sub n. And then it's 2n plus 2, where n is an element of the natural numbers. So that's one of the big differences now. All right. Our domain is not all real numbers. And we write the function of the rule of sequence slightly differently. We write it as a subscript instead of parentheses x. Yeah. If it works for the first 3, generally it'll continue to work for after that. The ones that you're going to see, that's probably a good rule of thumb. But in life, crazy things can happen. Can happen, especially at the subatomic level. But we're not there, right? We're not there. Oh, okay. Yeah, that's next week. All right. Cool. Let's look at example 2. Notice that this one looks a little bit different. Instead of just saying a sub n equals 4n over 3 plus 2n, which would work, it's itself set off in braces. That's fine too. That's just shoring it up. Okay, so you can actually put the rule of sequence, which is the nth term. That's what this is called. This is the nth term, or the rule of sequence. It can be written with or without. There's slight variations, but they all mean the same thing. Okay, you're going to be in the context of a sequence. List out the first 5 terms, and then look at this. Now we're getting into the shallow waters of calculus here. Then the limit as n goes to infinity of the rule of sequence. Okay, let's list out the first 5 terms. So I'm going to say a sub n equals. What number do we always start with n? Because it's not given. 1, because that's the first natural number. 0 came much later. So what do we get when we plug in a 1? Our first term is? 4/5. Oh, nice. 4/5. Okay, boom. We'll call this, if you want, a sub 1. All right. Comma. 8/7. Dang, you're fast. Plug in a 2 and you get 8/7. All right. And then a sub 3. Let me catch up. 12/9. Okay. I'm still making my comma. Holy moly. And then a sub, plug in a 4, you get 16 over 8 plus 3 is 11. Okay. And then it said to list out the first 5 terms. So a sub 5, 20/13. Okay, cool. Now from here you could say either comma dot 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 and close it off like that. Now with that, let me kind of hide the rule of sequence, because this is where kind of the real fun is. If I had listed those 5 terms, would you have been able to figure out what the rule of sequence is? Oh, hell no. That's the attitude I love, right? Well, maybe not at first glance, Mason. A good 5 minutes is really all I'm asking. Okay. Now a minute per term. You can actually think about it as 2 separate patterns, right? One in the top. When n is 1, I have to get a 4, right? When n is 2, I have to get an 8. When n is 3, I have to get a 12. Oh, I think I could figure that out. And then when n is 1, I have to get a 5. So you could probably figure it out. Okay. Each of those are called arithmetic sequences. We're going to get to that here in a little bit. So having the rule of sequence is nice. It's really nice. Now, here's another thing. If you wanted to give someone this sequence as a gift, and you didn't want them to get frustrated with how to generate the next term, like they didn't see the pattern, you can actually, instead of closing off the sequence, you can put dot 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 comma, and then you can write the nth term there, 4 over n over 3 plus 2n, put another comma, and then dot 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 to show that it would go on to infinity. That spoils the fun for them. But it's a courteous thing to do, right? So what this does, and they're actually equivalent, what this does is it's kind of like it's giving them a sampling of what the sequence looks like. And then it's like, here, if you want more, generate it for yourself, right? Yeah. Whereas if you give it to them like this, it's just like, yeah, here it is. If you want it, you can make it at home. Here you're giving them samples, and then you're giving them the recipe, right? Yeah. Here's some cookie. Here's another cookie, a cookie, another cookie, and a cookie. And if you like those cookies, here's the recipe, right? Right. It's like here's a cookie recipe. Got it? Nice. And we list them with commas. Okay. All right. So far, so good. Now let's answer that last part. What then is the limit as n goes to infinity of a sub n? Well, guess what version of a sub n I'm going to put? I'm going to put the version that's the rule of sequence, 4n over 3 plus 2n. Because if I just look at this, 4/5, 8/7, 12/9, 6, would you be able to determine what those numbers are approaching? The top looks like it's getting bigger, and the bottom looks like it's getting bigger. But is the top getting bigger faster than the bottom? It sure is. In fact, after the first term, which is less than 1, the numerator quickly overtakes the denominator. So you might think from just looking at this sequence that because the numerator is getting bigger than the denominator faster, the sequence might approach what? Infinity would be the logical thing, right? Because we talked about that. Anytime the top gets bigger faster than the bottom, it goes to infinity. So that would be a natural assumption. But that doesn't quite ring true necessarily, because this is how it's getting bigger in the top. The same function. They're both linear, right? If I wrote this as the limit, that's supposed to be an m, as x goes to infinity of 4x over 3 plus 2x, you'd be all over that like white on rice or brown on brown rice or green on green rice. That analogy can really take on any color you want. What would the answer be?
Does it approach 3?
Yeah, I'm just saying, what if? I'm trying to tie it to previous knowledge. What if you had this? Like this was on the AP exam. If this is on the AP exam, you should have this answered in 2 seconds. Good. And that includes bubbling. The top goes to infinity. The bottom goes to infinity. You can either use L'Hopital's rule or just realize it's x to the first over x to the first. And so it's leading coefficient over leading coefficient. Yes. Yes. Or you could say lop it, right? Lop it, which would be the limit as x goes to infinity. The derivative of the top is 4. The derivative of the bottom is 2. And now you get 2, right? You should get 2. Is it any different when we have n as a natural number rather than a real number?
It's not 0 over 0.
It's not. No, it's infinity over infinity. What's the reciprocal of 0 over 0, Hank? Infinity over infinity. Those are the two forms where L'Hopital's rule works. Okay. This is actually, for the same reason, this is 4 halves or 2. Okay, everyone there? So it doesn't go to infinity. These ratios will get closer and closer to 2. All right. So see why mathematicians at their most esteemed, I guess, gift that people appreciate is recognizing patterns. Because if you can recognize a pattern and come up with an explicit formula, then you can make sense of the world so much more assuredly, right? Instead of saying, it goes to infinity, it's like, contraire, it approaches 2. Right? Was that like a lamb? Math. Okay. Hey, anytime we celebrate math and there's some kind of big moment for math, feel free to all just bleat out math. Right? Math. No. That's different. That's slice minus lift. Okay. Here we go. Fact, right? Fact. Another name for a mathematical fact is theorem. Let A sub n be a sequence of real numbers. Okay. Now, by real numbers, what do I mean? I mean that the outputs can be real numbers. The input is still n, the natural numbers, right? The domain, the input n is natural, but the output can be any number. There's 3 possibilities when you take the limit as n goes to infinity. They can either get infinitely large, like we originally suspected, towards infinity, in which case we say that the sequence diverges. That's an important word that we're going to be using quite a bit. Just think of diverges. Diverges means to go away from, doesn't it? 2 woods diverged in the road. This is why I'm not Robert Frost. 2 roads diverged in a wood. There you go. That means the path became 2. They started separating from each other. Diverges means to go out from, away from. So when something doesn't approach a number, we say it diverges. And so something can diverge to infinity, or if the limit is negative infinity, it gets infinitely small, we say it diverges to negative infinity. But in our case up here, the limit was 2. So this sequence converges. That's the word that we're using. Okay. We say it converges to that number. So our sequence up here converges to 2. Converges means to get, closer and narrower, right? It gets closer and closer to 2. Will the sequence ever reach 2? No, it just gets closer and closer to it. Okay. And then the fourth thing that really won't happen in here necessarily, but just like with our limits, we saw oscillation. You could see it oscillate between 2 fixed numbers. Then we say it diverges not to infinity or negative infinity, but rather by oscillation. Can someone give me an example of a sequence that diverges by oscillation?
Tangent. No, see, sine. Anything but tangent, actually.
Yeah, yeah, that bounced back and forth. Yeah. But we're talking about, remember, we can just list the sequence, can't we? How about -1, +1, -1, +1? What would the next one be? -1, +1. So in this case, I needed 4 terms and I put ... Is that sequence going to converge? No. Will it diverge? It will diverge, but not to infinity. That's not going to get infinitely large. It's not going to diverge to negative infinity. That one diverges by oscillation, right? It oscillates between 2 fixed points. Can you write a formula for that?
Yeah, sine of x. If we're counting by
Ah, sine of pi halves n.
He knew that.
Is that right?
Yes.
Well, let's see. When n is 1, we get sine of pi halves, which is 1. Oh, how about negative sine?
-2.
Now, when n is 2, what do we get? Here's where you got to be careful. When n is 2, we made the correction of a negative. When n is 2, we get sine of pi, which is what? Sine of pi is 0. Cosine actually works nicely. But how do I go from n? If I did 3, right? If I did 3 pi halves would be -1. And then if I did 5, it would be 5 pi. I want those n's to be odd numbers. So how do I make it odd multiples of pi halves? 2n was even, right? What if I put +1? Or in this case, 2n -1. There we go. So yes, if you look at odd multiples of pi halves, that works. I was thinking something as simple as like -1 to like the n plus 1. Right? Will that work? Will that work? Test it out for me. That will not work, because when I plug in a 1 for n, what's my first term? +1. I have these out of step with each other. Guess what I have to do? Just take away the +1. Now will it work? Yes. Those little fine tuning adjustments, n plus 1, n minus 1, or n, those are going to become very, very important. All right. We're going to define exclamation point next time. Your worksheet is out there. It awaits you.
I'm missing 3 days of class.
You'll have 3 days of videos to watch, but they'll be fresh. Bye, Ellery.
Bye, guys.